This is part 2 of the lecture on section 1.3 on the greatest common divisor and Euclid's algorithm. We want to turn from examples now to proving a new theorem about the greatest common divisor. We claim that the greatest common divisor of A and B can always be expressed as a linear combination of those integers A and B, and furthermore, it is the smallest positive linear combination of this form. The way we'll prove that is to consider the set of all possible linear combinations of A and B, where the coefficients on A and B are integers, and where the linear combinations are strictly positive. We'll do this by applying the well-ordering principle to select the smallest of these linear combinations. Before we can do that, though, we need to prove that the well-ordering principle applies. It applies if we can show that S is a non-empty subset of Z that is bounded below. Well, first of all of M, A, N, and B are integers. Therefore, MA plus NB must be an integer, and S is certainly a subset of the integers. Secondly, we've constructed the set in such a way that it has an automatic lower bound, 0. Now, finally, we want to show that S is non-empty. We can do this by selecting M equals A and N equals B. In that case, MA plus NB is A squared plus B squared, which must be strictly greater than 0, because we have assumed we do not have the case where A and B are both 0. Therefore, the sum of the squares must be strictly positive. Well, that tells us that S is non-empty, and the well-ordering principle applies. Since the well-ordering principle applies, we're justified in saying let D be equal to the minimum of this set of linear combinations, and we want to prove that D is equal to the greatest common divisor of A and B. We're going to do that by showing that D is both less than or equal to the greatest common divisor and greater than or equal to the greatest common divisor. To show that D is greater than or equal to the greatest common divisor of A and B, we're going to argue that the greatest common divisor divides D, and therefore, using our previous lemma, the GCD is less than or equal to D. Well, we know that D is an element of S. Remember, it's the smallest element of S. Therefore, there have to exist integers M1 and N1 satisfying D equals M1A plus N1B, because that's what everything in the set S looks like. Therefore, since GCD divides both A and B, it must divide this linear combination of A and B. That is what we called Theorem 1. And so applying the lemma we just proved in the last part of this lecture, we know that the GCD of A and B is less than or equal to D. Now let's show that the inequality can be turned around. D is less than or equal to the GCD of A and B. We're going to do this by applying the division algorithm to first A and D. A must be equal to some quotient times the divisor D plus R. Now we want to ask ourselves this question: could R be positive? The answer must be no, because we can write D as a linear combination of A and B. We can now rearrange to obtain this form. But remember, R is the remainder we obtained from the division algorithm. Therefore, R must be greater than or equal to 0, and it must be strictly less than D. If R is strictly greater than 0 and less than D, we have exhibited an element of S that is less than D, even though D is the minimum of S. Well, that would be a contradiction. So it must be the case that R is strictly equal to 0. This tells us that D divides A. We can apply this argument again. This time, instead of working with A and D, we can work with B and D. By a sequence of steps that's exactly parallel to what we have above, we'll show that D divides B. If D divides A and D divides B, we have D as a common divisor of A and B. If it's a common divisor, then D must be less than or equal to the greatest common divisor of A and B, and that gives us the inequality we need. We've shown then that D is both less than or equal to the GCD of A and B and greater than or equal to the GCD of A and B, and therefore D must be equal to the GCD of A and B. But that, of course, is what we wanted to show, and that completes the proof of Theorem 2. We obtain a very useful corollary then. We've shown in the previous theorem that the GCD of A and B is the smallest of all the positive linear combinations of this form, MA plus NB. We now want to show that the only linear combinations, MA plus NB, are in fact multiples of the GCD of A and B. Let X be some one of these linear combinations. We first want to show that D, which is the GCD of A and B, divides this linear combination X. Well, the greatest common divisor is, after all, a common divisor, so it divides both A and B. But if D divides both A and B, we can apply Theorem 1, and that takes care of this part of the proof. Now let X be some multiple of D. We want to show that there are integers m and n satisfying the equation x equals ma plus nb. This isn't hard. The main theorem justifies the fact that the greatest common divisor D is equal to m1a plus n1b for some integers m1 and n1. Multiplying through by k, we see that if we select m to be km1 and n to be kn1, we have the desired linear combination. Therefore, any integer that has the form ma plus nb must be a multiple of the greatest common divisor of A and B. We can now solve the two problems that we posed concerning linear Diophantine equations. Let's look at the first one. Can we find integers x and y so that 2462x plus 462y is equal to 11? The answer is no. By the corollary, 2 has to divide every one of these linear combinations, but 2 does not divide 11. This tells us that our Diophantine equation has no integer solutions. In the first part of this lecture, we showed that 2462 times 2 plus 462 times minus 405 is equal to 2. We did that by computing the greatest common divisor of these two integers and then working the Euclidean algorithm backwards to arrive at this expression for 2. If we multiply this equation through by 6, we'll have the 12 that we require on the right-hand side. In the first part of this lecture, we showed that 2462 times 76 plus 462 times minus 405 is equal to 2. We did that by computing the greatest common divisor of 2462 and 462 by the Euclidean algorithm, and then working backwards through the process to come up with this equation. Once we have that, we see that if we need a 12 on this side, which is the equation we're trying to solve, we need merely to multiply this by 6. Then we multiply the left-hand side by 6, distributing the 6 to the two terms. 6 times 76 is 456. 6 times minus 405 is minus 2430. And that gives us one solution to the Diophantine equation that we've set here. Now, if we could come up with any other choices for x and y, so that this would sum up not to 12 but to 0, we could add those values of x and y to the 456 and the minus 2430, and we'd have yet another solution to the 12. Let's see if we can solve that equation. It's easy. We put this on the other side and divide through by the coefficient on x. Since we already know that the greatest common divisor of these two integers is 2, it makes it easy to reduce the fraction. And now we're going to write the solutions to this homogeneous equation in a convenient way. If we're going to get integer solutions, we're going to need our y to be a multiple of 1231. So we set y equal to 1231k. Substituting that into the equation above, we see that x would have to be minus 231k. This gives us a general solution to the Diophantine equation. X is any integer of the form 456 minus 231k. Y is minus 2430 plus 1231k, where k is any integer. We don't need to do this, but if we wanted to, for assurance, check our solution, we could try setting, for instance, k equal to 1 in these two expressions, and we'd get x is 225 and y is minus 1199. If we plug these two values back into the expression 2462x plus 462y, we do in fact get 12. And in fact, we'll always get 12. This then is the set of all possible solutions, and they're guaranteed to be integer solutions as long as we're choosing k to be an integer in this pair of equations.